Welcome to the first lecture of our course which is titled as Introduction to Chemical Thermodynamics and Kinetics. We will first give you a brief history of classical thermodynamics to begin with. Now, when we start teaching thermodynamics or talking about thermodynamics or chemical kinetics, let us first discuss what physics is all about. Any physics or any physical science or physical chemistry deals with constant interaction between energy and matter, because matter and energy are constantly interacting between themselves. Now, the question is at what level you want to understand or study this interaction. Now, you can think of energetics which is a time independent process, and you can also talk about kinetics or how this exchange of interactions is happening with respect to time, where you talk about the rates, which is an inherently time dependent process. Now, the question is how do you propose a model that will satisfactorily explain the phenomena which we observe. Now, interestingly, thermodynamics or chemical kinetics or the classical thermodynamics was developed in the same way, where people tried to explain something which is a phenomena, and they tried to develop an approach which is known as phenomenological approach, where you observe a particular phenomena and you try to explain it based on some logical footing. The same way chemical kinetics was also developed, and but here the important thing here is you do not need any fundamental understanding or any understanding of how the microscopic world looks like. Meaning you can actually describe the entire thermodynamics and chemical kinetics in a macroscopic way, where it is not necessary to build a model of microscopic understanding. For example, how a material or how a matter is made up of. We know that matter is made up of atoms and molecules, but that concept is not absolutely necessary as long as we are dealing with explaining some experiments which are macroscopic in nature. Now, similar concept also applies to reaction kinetics. So, our understanding of the microscopic world has been started with the development of quantum mechanics, and there we talk about again time independent processes, where we talk about the energetics or the energy levels of atoms and molecules. Similarly, you could also ask how these molecules interact with themselves, and when they say for example collide with themselves among themselves, how one molecule transforms into another molecule, and that is the basis of chemical reactions. And you can ask this question, what is the time dependent process and how a particular molecule evolves into another molecule, then you talk about the dynamics of the process, that is also inherently dynamics. So, what I have seen on what I have shown on this slide, you can see here that you have 4 quadrants. On your top left quadrant, we are talking about the energetics, which is the content of this course or the major part of this course, which is classical thermodynamics. And on your right hand top side, you see the position of chemical kinetics, where we will be discussing with kinetics again from a microscopic phenomenological point of view. And the horizontal line actually differentiates between this macroscopic approach and the microscopic approach, whereas the vertical line differentiates between the two other approaches, like whether you are talking about a time independent process or a time independent process. Now, our fundamental understanding of microscopic world is dependent very much on the studies of spectroscopy. By spectroscopy, it can be optical spectroscopy, it can be other forms of spectroscopy. When we shine some light on the molecules and we know that molecules have particular energy levels, so then you will actually see not a continuous absorption from these molecules, but discrete lines in the absorption or the emission spectra, and that is how quantum mechanics was emerged. And there we again talk about time independent formalism of quantum mechanics, where we talk only about the energy levels of atoms and molecules. We could also talk about time dependent formalism of spectroscopy when we want to study something like reaction dynamics. Now, the bridge between this macroscopic realization and this macroscopic observation is statistical mechanics, and similarly Just like we discussed the time independent process, we can have an equilibrium formalism of statistical mechanics, where you talk about the energy levels of atoms and molecules, and then you ask, can we actually build up from this fundamental principle or in an ab initio way all these macroscopic variables or observables or all these thermodynamic properties, and that connection is equilibrium statistical mechanics or equilibrium, sometimes we call it as equilibrium thermodynamics. Similarly, you could have a non-equilibrium formalism of thermodynamics, where you start with the molecular reaction dynamics starting from the time dependent quantum mechanics, and then you can actually explain the rates of macroscopic processes which you had already described phenomenologically. So, this slide describes the overall picture of how one can actually take a macroscopic approach versus a microscopic approach to describe either a time independent processes or time dependent processes. Now, we will restrict ourselves to this section which I have highlighted here. So, we will only discuss about classical thermodynamics, where the understanding of the microscopic world or the understanding of the very much working of how the microscopic world is not absolutely necessary. However, we will give you some examples just to clarify a few concepts, where we will use very brief idea or very preliminary ideas of quantum mechanics, and then we will explain some of these phenomena. Similar things also happens for kinetics. We will be only discussing with the classical kinetics or the phenomenological rate equations, and try to describe the reactions or chemical reactions in terms of a macroscopic viewpoint. Now, to talk about the classical thermodynamics or the development of classical thermodynamics, we will mostly describe the core years, meaning 1823 to 1882, where major developments in thermodynamics happened. Now, the concept of heat and work was already established, and then I mean by 1600 or so, but we are choosing this particular period because the reason is during this period a lot of great minds appeared in the history of science, and they contributed a lot in the development of thermodynamics. Now, thermodynamics is one of the very classic subjects in the sense that its foundations are very strong, and it is an very much experimentally driven science. People did some experiments and they observed something, and then they formulated all this observation by a set of very simple laws, which we will be discussing throughout this course. Now, to begin with, we will start with a quote by Albert Einstein, and he once said, "Thermodynamics is the only physical theory of a general nature of which I am convinced that it will never be overthrown." Now, this statement shows how rigorous or how strong thermodynamics or its logics are built in. Now, as I said that by 1600 already the concept of heat and work was established, but around 1700 or so there was a theory called Calorie Theory, which used to say that heat is a form of fluid that transforms from one body to another body, and the presence or absence of the caloric actually dictates the temperature of the body. Now, although there are some experiments which refuted the caloric theory, most of the people were or scientists were actually accepting that theory at that point. And then finally in around 1798 or so, Benjamin Thomson, who is also known as Count Rumford, did a fantastic experiment. What he did is that Rumford observed that when he was boring the cannon or making the barrels of cannon by making holes inside that piece of metal, he found that a lot of heat is generated, and he devised an experimental arrangement where he connected this bore of the cannon to a bucket of water, and he found that actually water boils. From that he concluded that there is a mechanical equivalence of heat. Now, this try to realize is very important concept, because earlier people used to think that boiling of water is possible only in the presence of fire, and Count Rumford showed that no, actually you do not need fire. Even a mechanical work which is just the boring of a cannon can actually produce enough heat that can boil water. And this was a very important concept, but which actually refuted caloric theory. But the final disposal of the caloric theory came with the experiments by James Joule, and who again made a very nice experiment. So we will discuss this experiment in detail when we will be discussing the first law of thermodynamics. And Joule actually made an arrangement where he was making lifting or actually falling some weights in the surrounding, and that weight was connected through a wheel to a paddle system, and if the weight actually falls from a higher altitude to a lower altitude, then the paddle will rotate, and that will increase the temperature of water within which the paddle was immersed. And from this experiment, Joule very convincingly proved that there is a mechanical equivalence of between heat and work, which means that if I do some mechanical work, which can be a pressure volume work, which can be a displacement work, which are all connected, that can also produce heat, and that can actually to warm up water. It is similar to what Count Rumford did, but here actually from these experiments, Joule also quantified the pressure volume work with the with the amount of heat produced, and which led to the formulation of first law of thermodynamics. Now, by 1840, it was very well known from Joule's experiment that this caloric theory is wrong, but around 1950s, then two great figures in thermodynamics appeared, Rudolf Clausius and William Thomson, who is also known as Lord Kelvin. So they theoretically or basically formally derived all these or formulated all these laws into two basic laws, which are known as first law and second law of thermodynamics, based on the experiments of Joule and Count Rumford. And the second law, they actually the second law actually stemmed from the experiments from a French engineer named Sadi Carnot, which will be discussing about those experiments when we discuss about the second law. Now, Carnot's experiment was done long time back in 1824, but nobody actually realized that time that the importance of his work. And later on, Clausius and Kelvin, they revived Carnot's work, and they said that this is the foundation of the second law of thermodynamics. So Clausius and Kelvin had several statements of on the laws of thermodynamics, which are of course equivalent statements, and we will be discussing about those statements of first law and the second law. There is also a law called the zeroth law of thermodynamics, which was actually realized later, that the more fundamental thing other than the first law or the second law is the concept of temperature, that if two bodies are of same temperature, or there will not be any heat flow between them, or two bodies are in thermal equilibrium, they will have the same temperature. So that was realized much later, and that is why by that time already Clausius and Kelvin talked about first law and second law, and people realized that this concept of this temperature is more fundamental. So let us call it as a zeroth law, because already people have chosen the names first law and second law. And there is also another law of thermodynamics, so which is third law, which we will not be discussing in this course, that talks about the irreversibility of a process, or the spontaneity of a process, that was developed by Nernst. And then interestingly, around 1860, Clausius gave the fantastic concept of a state function, which he called as entropy, and he showed that for any irreversible process, which are any spontaneous process is by the way irreversible in nature, he showed that you can think of that the entire system or entire process will happen if the entropy of the universe is ever increasing. And that is known as Clausius inequality, which also will be discussing in detail how we can actually derive the Clausius inequality from Carnot cycle. Now, parallel to the thermodynamics also came the kinetic theory of gases, which was very, very important, because in many cases we will be giving the examples based on very simple system or very simple idealized system, like a ideal gas confined in a container. And for that development, the first formalism again was given by Rudolf Clausius around 1857, but he basically revived a very early work by Daniel Bernoulli another French scientist, who did all this important work on kinetic theory of gases around 1738 or so. And there are also parallel development, if you remember from your high school studies, like Boyle's law and Church's law, and also the combination of this Boyle's and Church's law to get these universal gas law, which was applicable for ideal gases only. And then people also realized the deviations from ideal behavior, and where people proposed many models that also we will be discussing in this course. Now, for around 1860 or so, stemming from this kinetic theory of gases, Maxwell gave the idea how one can calculate the distribution of molecular speed, because kinetic theory says that a gas molecule, a gas actually a macroscopic system is composed of molecules which are in random chaotic motion, and that how will you describe the motion of these molecules, and how will you get a formula to describe what is the average speed of these molecules for a particular temperature. That actually you can derive from using the prescription by Maxwell, and later on two important theories were put forward by Ludwig Boltzmann, and he found that you can actually start from Maxwell's distribution of molecular speed, and you can show that the entropy, some quantity which is equivalent to entropy, can actually increase with respect to time for any equilibrium or non-equilibrium system, and that was the catch in Boltzmann's theory, and that is usually known as H theorem. But there was an inconsistency initially, because Boltzmann's theory fundamentally assumes the reversible nature of collisions. Then it predicts or then it predicted that actually a spontaneous process can also be run in the reverse direction, which is contradictory with the Clausius statement that any spontaneous process entropy should increase entropy of the universe. So, to survive his model, Boltzmann later on put forward another important concept in statistical thermodynamics, which is known as concept of ergodicity. We will not discuss these theories in detail, because we will be only confining ourselves to the macroscopic description of matter and energy. And then this is just to let you know that along the same line, along 1900 or so, Willard Gibbs put forward his very monumental work on classical statistical thermodynamics, where he introduced the concept of ensemble. And what he said, the essence is that if you look at a macroscopic system, and if you think of there are many microscopic systems are composing this entire macroscopic system, then every microscopic state, if you watch a particular microscopic state or realization of the system over time, that will actually you can actually think of that this time averaging over a sufficiently long time of any microscopic realization of the system, essentially equivalent to saying that we are doing all this macroscopic measurement. So, this will happen only for if the ergodicity concept is correct, and Gibbs very correctly showed that there is an alternative approach to statistical thermodynamics, which is known as ensemble approach. And later on, so Gibbs formulated the thermodynamics in his own way, but he gave the full credit to Clausius. And there are many controversies on this particular aspect, who is the father of thermodynamics, because some people say that the work actually is inherent in Count Rumford's work, and some people say no, actually the work was actually the main work was done by Sadi Carnot. But what let us see what Willard Gibbs said. He said, if we say, in the words of Maxwell some years ago, around 1878 or so, that thermodynamics is, and he quotes Maxwell, a science with a secure foundation, clear definitions, and distinct boundaries, and as those formalism were laid, these definitions fixed, those boundaries traced, there can be but one answer, and that one answer, he said, is certainly not before the publication of the memoir. And this memoir was published by Rudolf Clausius in 1850, where he revived Bernoulli's work, where he revived Sadi Carnot's work, and he basically formulated the entire thermodynamics or classical thermodynamics, the way we look at thermodynamics in today. Now, this particular work of this Gibbs and others laid to foundations of many other branches in science. For example, this ergodicity was later on rediscovered or reformulated by Enrico Fermi, who was working on some coupled spring problem, and he was trying to see how if the ergodicity is valid, how the energy is if I dump energy in a particular spring which is connected to many springs, how the energy flows. And he accidentally discovered that actually the energy does not flow in a unidirectional fashion, the energy actually comes back and forth and then eventually flows. And what he basically discovered is a recurrence phenomena, and which in today's modern language we call as the formation of solitons. And parallel to this, there are a lot of interesting discoveries in information theory which are particularly important for computation and the development of the computer science as a whole. And then around 1940s, Shannon gave a very brilliant idea how we can actually connect the Boltzmann entropy with the information content, and this is known as information theoretic approach of entropy. Now, we will not discuss all these things, this is just to let you know that the classical idea which was developed by Clausius, Kelvin, extended by Boltzmann and then by Willard Gibbs, how it also shaped the future of many other areas in modern science and technology. Now, we will give you a very brief outline of chemical kinetics or the classical chemical kinetics. Now, compared with chemical thermodynamics or classical thermodynamics, kinetics is more or less a newer field, in the sense that although the concept that if we want to study the process or the rates of some processes, we know that at any instance the rate will be proportional to the activity or the concentration of the substances, which is known as the law of mass action, which was put forward by Wajh and Goldberg way back in 1864, but it was not very much realized that time. The first realization or the first logical formulation or foundations were put forward by Jacobus Van 't Hoff, and who published a book on his monumental work on thermodynamics and chemical kinetics in 1884, and that is kind of the beginning of the modern research on chemical kinetics. Van 't Hoff, by the way, was the first recipient of Nobel Prize in Physics in 1901, and the citation says, in recognition of the extraordinary services he has rendered by the discovery of the laws of chemical dynamics and the osmotic pressure in solutions. Now, we will be discussing some of Van 't Hoff's work, particularly his fantastic work on how chemical equilibrium can be modified, or the equilibrium composition can be modified by application of temperature, which is known as Van 't Hoff equation. Now, later on around 1889 or so, Arrhenius gave a very important concept. He studied experimentally many reactions, and he was trying to find out how the rate constant of a reaction varies with temperature, and he came up with a phenomenological equation where he tried to explain everything or the variation of the rate constant with temperature by introducing a concept which is known as energy of activation. Now, this was a very important concept, because he said if you have reactants, say A and B, that will not readily give the product until and unless they cross some energetic barrier, and this barrier exists, we know, and today we call it as activation energy. And this actually stemmed only from Arrhenius's experiments, and that explanation for activation energy, or how one can actually include that very cleverly in a model of reaction dynamics, came much later though. Now, along the same time, people were also interested in devising some mechanism of the reactions. By mechanism, again, it is not a microscopic approach, it is again a macroscopic approach, where you say that a particular reaction is actually a composite reaction which can be decomposed into many elementary reactions which cannot be further decomposed, and all these elementary reactions together constitute the macroscopic or the composite reaction that we observe in reality. Now, the first such approach actually was applied in a real life example on enzymes by Michaelis and Menten in 1913, although the concept of chemical reaction mechanism was not very popular by that time. But Michaelis-Menten's work actually predates in that sense the chemical reaction mechanism, and they showed that how one can conceive a very simple mechanism to understand the initial rates of enzymes, how it varies with the initial substrate concentration. So, when we will be discussing the kinetics part, we will be discussing this Michaelis-Menten model in to some much more detail. And around 1920s or so, Erwin Langmuir first came up with the idea how during a reaction between a gas and in presence of a solid surface, one can conceive the idea of adsorption. Now, it is different from absorption in the sense, in absorption molecules actually penetrate the surface and go inside the bulk layer, but what Langmuir gave a concept is the molecules are only stuck on the surface, and that led to the new field which is known as surface science, which was later extended by the American physicist Cyril Hinshelwood. And that is many people think that this is not only the birth of the chemical the surface science, it is also the birth of the chemical kinetics in general. And later on two scientists, namely Cyril Hinshelwood and the Russian scientist Nikolai Semenov, they did a monumental work on this reaction mechanism, how one can actually formulate composite reaction and then get all these elementary reactions very logically and try to explain the entire reaction mechanism by adding all these elementary reactions. And Hinshelwood and Semenov got a Nobel Prize in chemistry for this particular work, where they mostly studied what is known as chain reactions. And then I have written here few historical things which were followed, but this list is really endless, particularly when you talk about chemical reaction dynamics. The first conclusive or convincing theory came around 1935 when Henry Eyring, Michael Polanyi and Meredith Evans came up with this concept of transition state theory. We will not be discussing the transition state theory in this lecture because it requires some knowledge of statistical thermodynamics, but we will be discussing an alternate approach where you can actually use Maxwell-Boltzmann distribution and just consider the collisions among the gas molecules, and thereby you can say that how this you can actually formulate or devise the rate of the reaction. And we will also we will just conclude our historical or the chronological development here. So, in the next lecture, or which will be the first lecture of this course, we will start from we will start from some basic concepts, but before that of thermodynamics, but before that we will first start with a review of the kinetic theory of gases, how you can not kinetic theory, how you can actually formulate the gas laws, the ideal gas law, and also the deviation from the ideal behavior, and how one can actually formulate the equation of state for a real gas. Those things we will be first discussing, and then we will be discussing the first law, and then the applications of first law, and then second law, and in that we will approach. So, to summarize, in this lecture we gave you a brief overview of classical thermodynamics and classical kinetics. Again, we will end where we started with. Remember, we said we just started this discussion with a beautiful statement by Einstein, and who said that thermodynamics is perhaps the only general theory that will never be overthrown. So, you should always keep that in mind, that there has been a lot of theories which has been invented, like quantum mechanics and many other things, which has changed our concept or regarding the perception of this nature of the universe. However, thermodynamics is still the laws of thermodynamics still holds, and they are just unrefutable. They through the work of Clausius, Gibbs and many others. So, we will see how this formalism got developed, and we will be discussing throughout this course about this about thermodynamics and classical kinetics, but we will be considering mostly the applications in chemistry. Thank you.